In this episode of The Embedded Insiders, Brandon and Rich discuss Silicon Laboratories' recent divestiture of its infrastructure and automotive business units to SkyWorks Solutions. The sale includes the company's power, isolation, broadcast, timing, and other products and IP. Silicon Labs CEO Tyson Tuttle said several years ago that the company is all in on IoT, and this move appears to be him keeping his word. But was it the best move? Afterwards, Rich is rejoined by Zane Tsai, Director of the Platform Product Center at ADLINK, and Amit Goel, Director of Product Management for Embedded AI Platforms at Nvidia. After discussing enabling technologies in previous episodes, the three get down to how this functionality can be applied to autonomous mobile robots. The market opportunity for AMRs is vast, but so are the challenges. The three dive into a collaboration between ADLINK, Nvidia, and BMW, which increased productivity, improved efficiency, and reduced costs in the German automakers' manufacturing facilities. Finally, Perry Cohen investigates the long tail of the ongoing semiconductor shortage and how market dynamics that limited the supply of multi-layer ceramic capacitors back in 2018 are playing out again in the broader electronics market. Of all the sectors feeling the squeeze, none has been pinched more than automotive. Why is that? What can be done about it? And how long until things are back to normal? Richard Barnett of Supply Frame helped explain that our definition of normal may need to change. Hello and welcome to another edition of the Embedded Insiders. I'm Brandon Lewis, Editor-in-Chief of Embedded Computing Design. I'm here with Rich Nass, who is the Executive Vice President and Brand Director of Embedded Computing Design and Open Systems Media. How you doing, Rich?
I'm fine. If you go back like a year or so and listen to these podcasts, you were far more excited in the intro than you are now.
Hello and welcome to the Embedded Insiders. I'm Brandon Lewis, Editor-in-Chief of Embedded Computing Design, and I'm here with Rich Nass.
That's more like it. Thank you very much.
You're welcome. I wasn't giving you the introduction you deserved.
Thank you. And was a very exciting week here in Florida. I got a haircut.
Oh, so lots of scuttlebutt down at the old barber shop. What'd you pick up from the guys in the next chair?
Well, I did hear some very interesting news. I would say I got it in the barbershop, but I didn't. I actually got it in my inbox. Silicon Labs making more moves. They are certainly an interesting company. No moss growing there for sure.
No.
They actually moved some of their moss off to SkyWorks.
And the moss was there. Was it the entire automotive business?
Well, the way that I'm reading between the lines, it's the automotive and the infrastructure business, which to me is all the non-MCU related IoT stuff. Like, I'm assuming that they kept the smart buildings, which to me is infrastructure, but I don't think is to them. I think it's the power related stuff that has to do with infrastructure and automotive. That's what the part that SkyWorks would want.
Mm-hmm. Yeah, I saw that they moved a lot of their power stuff, the automotive stuff, the network infrastructure, enabling technologies there. Not so much like networking in terms of short range wireless, like they're a big player in with Bluetooth and Z-Wave and Zigbee and all that, but all the stuff that makes, a network tick.
They said a while ago they were going to be all in on IoT, and man, they really have been true to their word. They are all in on IoT and getting rid of anything that's not IoT.
Well, there are a couple of interesting parts of that. Just from a high level, automotive floated Silicon Labs boat for a long, long time. That was a bread and butter market for them. Give them a fighter's punch. And actually,
but they got a lot of bread for that stuff.
Yeah, that's true. That's true.
They got, it's multiple B words.
Yeah. Yes. But it's an interesting move, and it's also interesting when you consider the fact that even within automotive, that if you're talking about connecting to sockets for IoT, that's a lot of sockets there as well. And relinquishing some of the capabilities inside automotive, depending on who you ask what IoT is, that may be a significant piece of the pie.
Yeah, that's the way that I read it. You know, I'm always the devil's advocate guy, and I'm thinking, well, the automobile is just a moving IoT socket,
Hmm.
and I would think that they'd want to keep that. And that's when I sort of dug into it a little deeper, and I couldn't get too deep because the information is so new. But that's why I think it's has nothing to do with the um, data transmission part of the automobile. I think it's more the powering the automobile that they're letting go of.
That being said, I mean, the more footholds you can get inside a car, the better. You know, there's so many electronics going into a car right now, and if you can make up a little bit of profit here from there, you know, all the better. That market is crazy intense, and when it comes to pricing and commoditization. And another interesting point is the car may be a moving thing, but it's really a lot of moving things, plural. You know, the number of different endpoints that you could have in an automobile is growing exponentially. All of the different ECUs that control various subsystems and subdomains of the vehicle themselves are all candidates for being updated in different ways, pushing back tons of data into the cloud. So, yeah, I mean, I think when we're talking IoT, like we said, IoT means many things, to many people. To Silicon Labs, I think it means the more traditional IoT, smart home, smart building. You know, make your lights turn on and stuff.
There you go. So if we're going along this theme of automotive, I just had an interesting conversation with one of the power semiconductor vendors, and the traditional EVs are running at 400 volts. I was not aware that Porsche has, is it Porsche or Porsche? Porsche. Their EV runs at 800 volts, which I thought was pretty interesting. You know, for a lot of good reasons why you do that, except that what happens when I want to charge that in my garage? Now I
Yeah,
got to get this super duper charger that's pumping out 800 volts.
I think that's the point. You know, I'm doing some remodeling here at my house, and I had to do a little bit of electrical. And the electrician came in and he was like, "Hey, you know, I could add a couple of outlets in your garage, and I could also wire it up for one of those Tesla charging stations in the future." And I said, "Well, you know, I'd like to get a Tesla one day, but I'm not there yet." But you know, Tesla does sell those individual charging stations for your home. And it sounds like that may be a proprietary play that a lot of the auto manufacturers who are going into the EV space are going to pursue, given the fact that there's just not the infrastructure out there right now.
Yep, I would definitely agree. That's funny. When I had my home project done, I ran coax all through the house.
Coax. What's
Yeah.
coax?
Something you don't use anymore. And it wasn't that long ago.
One thing I will add, you know what? I remember when we talked to Jim McGregor at the end of last year, when after all this Nvidia and ARM stuff was going on, the AMD Xilinx stuff was going on, he specifically said the next M&A to happen is probably going to be in that RF space with somebody like SkyWorks. So prophecies coming true. We're
Damn.
like, you have to listen. If you're listening right now, you need to tune into every episode of the Embedded Insiders so that you can know the future like we do.
Did you buy the stock?
Of Embedded Insiders?
Forget it.
No, I didn't. And I always wonder, I'm like, would that be illegal for us to do? I mean, we're privy to a lot of conversations with a lot of things that are off the record. And I don't think the SEC is watching, is watching what I do, but would that be insider information? I don't know.
Embedded insider information.
Oh, there you go. Tune in next week for more embedded insider information. We'll tell you about the electronics market and where you should invest your tax return. Now, Rich is joined by ADLINK's Zane Tsai and Nvidia's Amit Goel, who take us into the world of autonomous mobile robots and Industry 5.0.
When you talk about Industry 5.0, which is obviously the follow-on to Industry 4.0, this is what I think Industry 5.0 really represents. It's the ability not just to have robots, but to have robots be able to function in an environment with people, to be able to operate safely and securely in environment to have mobile robots with people is really a heck of a lot harder than it sounds. So I'm going to start with Zane. If
Yeah.
you could talk about the design process of these AMRs, that would be a good starting point.
To design AMR, there are really lots of to consider about. So from some functional subsystem like sensor fusion or environment perceptions, visualization that includes machine vision and reasoning, the navigation systems like locationing, mapping, routing, motor control, the planning, communication subsystems. Sometimes if you try to control a robot arm, you have to consider about the emotions. And also occasionally, if you want to interact with the human, you have to consider about the human machine interfaces. And also as it's a mobile device with intelligence. So the power consumption and computation efficiency is also critical. So how you choose a proper processor to handle all these tasks, what kind of controller you're building with, that's some critical consideration you have to take into. Then you have to integrate those units under a logic. Then you can build your AMR. So to build an AMR from scratch is really complicated. Fair Friend Group, that's the third largest machinery group that they're trying to build industrial 4.0, 5.0 in their factory to provide a higher efficiency. And AUO group and the Foxconn group, they're also trying to deploy this kind of AMR in their factory because in the factory environment, the most important consideration for them is the expense saving. So this kind of autonomous mobile robot can further saving their OPEX a lot in the future. They're a robot don't complain, the robot don't absent, they don't take leave, they don't have romantic issues. So I think this kind of scenario is ideal for deploying the AMR in the first place because it's controlled and it's meaningful, and also we can actually see the benefit that brings from these AMRs. Luckily, with the technology advance, we have some open resources that already provide some level of integrations and make it programmable, like those popular SDKs like Rust. And the leading solution vendor like Nvidia, they also bring in the state-of-the-art supercomputer in the SON form factor that we call the Jetson, as well as the Isaac SDK that can you fully utilize it.
You brought up a really important point. The power in these AMRs, obviously they can't be plugged in. They can't be tethered with a wire as they're going around. So power is super important here. Let's talk about the Nvidia contribution here.
AMRs are extremely complex systems, right? They're integrating a lot of different sensors ranging from 2D cameras, time of flight sensors, LiDARs, IMUs, and all of these data that is from the sensors has to be processed in real time on the robot itself to allow it to autonomously navigate in the complex and dynamic environment of factories and warehouses. So to address that, we created Jetson, which is designed ground up with all the components that you need to build a complex solution like an AMR. It has all the high-speed IOs, so you can connect all these sensors. It has extremely high-performance computing elements, so you can process these things in real time, and based on that, control the robot. So with the Jetson platform, you get the compute, you get the SDKs that you need to build these things and deploy them at scale. Another key contribution that we are making to this development and deployment of autonomous mobile robots is a simulation environment. Developing these with actual physical hardware puts a lot of constraints on how quickly you can build these and how many people can be working on it at the same time. Once you move this whole thing into simulation where everything is photorealistic, all the things are physically based, then you can scale this out, your development to people anywhere, and you can do this in a safe and inexpensive manner. So we have created a simulator where you can actually model your entire warehouse, you can model the behavior of your mobile robot, and develop the brains, because all these robots are essentially software-defined machines now. They have great mechanicals, but the key thing that is happening from software and algorithms. And now putting this all in simulation really enables people to develop this at unprecedented speed.
A lot of what you've been describing is great when you're designing this robot. However, what do you do after it's deployed in the field? How do you make sure that it's actually operating the way it's supposed to?
For every AI project, you have to think about end to end because you have to continuously train things, you need to deploy them, and then go through this loop iteratively. The important thing with the autonomous mobile robots, which is different from the typical AGVs, is that they are smart, right? These are smart robots. They have AI capabilities. They keep learning, they get better with time. So the entire tool chain and the entire workflow of deploying, collecting data, monitoring these, refining this to actually update new models that can handle all your corner cases is an integral part of deploying an autonomous mobile robot.
When you deploy the AMR in the field, you have to consider what's his location and if he's performing the task as you instructed. And so the navigation platform itself is quite critical to tell where it's about. And also the fleet management system is supervising these AMRs in operation. But in between, these subsystems has to communicate with each other. So in navigation system, there's some algorithms being applied like a SLAM or triangular locationing. And the fleet management system that compose lots of other algorithms in scheduling and the monitoring for the tasks. And also this communication has to be real time. Otherwise, it has some occasion like unexpected collision or malfunction can bring some jeopardize in the whole tasks.
We've been writing a lot about this lately, and there's some confusion over, is it a CPU? Is it a GPU? Is it a TPU? Is it a VPU? What is the right choice here and why?
That's a very good question, Rich. Going back to what I said earlier, these machines are complex systems that have to do a lot of things, right? They have to sense the environment, then they have to perceive it. And based on the perception, then they have to act and control their behavior, right? And all of this requires a lot of software. And in order to develop that software, you need a platform that is flexible, that is highly performant, and that is easily programmable. And that's where GPU comes in, right? With over 1 million CUDA developers on our platform, the GPU is ideal for building this product. We recently had a big announcement with BMW where they're using the Jetson AGX Xavier as the brain of their smart transport robot, and they're using our Isaac software and a simulation environment to actually develop this, which is being deployed for their factories to bring parts from one station to the other. And it's doing this in an environment where there are people moving around, where the factory layout keeps changing because with an agile development customization that is needed, it's not the same parts being required for every car. Every car is customized, so you need to bring different parts. So it has to be completely done in real time, and it needs to align itself autonomously dock at that particular trolley. So identifying the pose of it, identifying the obstacle in its way, avoiding them. All of this is happening in real time. We're using the Jetson-based computer that is being deployed.
That's a collaboration between Nvidia, ADLINK, and the ADLWorks to build the AMR for BMW factory. That really brings a higher efficiency and higher safety standard to the factory. The Jetson's SOM is an really power efficient supercomputer that provide the abundant control and compute efficiency for the robot control, especially in those mobile devices. Its power efficiency is really great compared to other processors.
Yeah, our flagship product today is the AGX Xavier, which is offering more than 30 trillion operations per second of performance in just 30 watts. There is nothing out there that is available in an embedded form factor today, which is needed for, for building an AMR. The swap size, weight, and power is important, right? So Jetson brings all of that together in a form factor that is ideal for this application. Another reason why GPUs are so essential for this particular problem is because you have a really diverse set of things that you want to accelerate. You could use an ASIC to just accelerate your neural network, but what happens when you have to accelerate your planning algorithm? What happens when you want to accelerate your point cloud processing? So there are so many different pieces that need to be accelerated. And using the Jetson platform, we have integrated all the different heterogeneous components that allow you to process these things. So the GPU offers so much flexibility and so much performance that it makes it really easy for people to accelerate these applications, and they're not constrained in any form on what they can do.
It's time for Tech Market Madness, where Perry Cohen explores the ongoing semiconductor shortage and its pointed impact on automotive supply chains with Richard Barnett of SupplyFrame.
Back in 2018, the industry began struggling with a shortage of multi-layer ceramic capacitors. Consumer demand for smartphones, cameras, and more intelligent automobiles drove the need for more capacitors, which is great. Except, the market for the most common MLCC sizes and capacitance values had been almost completely commoditized over the previous 10 years. Without any profit margin left in their flagship products, MLCC manufacturers continued to add production capacity, but not for the most popular commoditized parts. They were seeking greener pastures in smaller case sizes and higher voltage solutions equipped with features like flexible termination that could capture higher profits. So, demand spiked, supply plateaued, and it got so bad that MLCCs had to be allocated, essentially rationed, across the industry. We're still dealing with MLCC shortages today, only now the shortage has spread and there is a major global shortage of semiconductors in general, which is hurting a number of industries, especially the automotive sector. But before we dive into specific verticals, what's this ongoing problem with semiconductor supply and demand? Richard Barnett, the CMO of market intelligence firm SupplyFrame, responds.
Longer-term cyclicality around major waves of capital expenditure investment going into foundry and fab capacity, and then that translating into sort of a ramp in general around new semiconductor products for different industries. And so, generally speaking, we were moving into a ramp up in 2020 anyway. While it was improving in terms of overall capacity at sort of the upstream fab level, there was potentially going to be a constraint in demand anyway, right? Just sort of a normal pattern that we've seen before.
So, it sounds like some of the same market dynamics in play during the early stages of the MLCC shortage have also been a factor in the limited availability of semiconductor solutions in general. I'm surprised the pandemic didn't have more of an impact.
This is before COVID and the pandemic was going to hit.
Oh, never mind.
But then enter the COVID pandemic, and what happened very quickly is that the demand mix across multiple industries shifted really fast.
Of course, all of this makes sense. The COVID-19 pandemic turned everything on its head, and the electronics market in general, and the semiconductor market in particular, were no exception. Just consider how your own routines changed from January 1st, 2020 to January 1st, 2021. Did you buy extra gear for your home office? Did you splurge on a nicer home entertainment system? How much more have you used Zoom since the quarantine started compared to before? How often did you drive to work, or anywhere? Now, multiply those changes in behavior across all of the professional households worldwide. Nestled in there was a clue as to what is happening in the automotive industry. People were barely driving, period, during the height of the pandemic, much less thinking about buying new cars. So as the pandemic ramped up, automakers scaled back vehicle production. But then something interesting happened.
For automotive, there was an immediate reset of forecasts in the March-April timeframe for the remainder of the year with still a great deal of uncertainty. And generally speaking, most automotive companies were ramping down their vehicle production forecasts somewhere around 40-50% for the remainder part of 2020. And then what happened is those decommits rippled back to major semiconductor suppliers that a lot of their catalog of parts, microcontroller units, et cetera, are standard components that can be used in other applications. And so generally what we saw is a play that you don't see very often of a dramatic shift in capacity allocation and consumption across industries, where that decommitted demand in automotive was shifted very quickly into other industries, primarily consumer electronics and enterprise data center.
If you don't use it, you lose it. But what happens when you're ready to start using it again? That's where allocations come back into play. Nobody likes them, but there's really no fair alternative. Still, that has made getting back to normal difficult for the automotive industry, whose electronic consumption today could be described as a mile wide but an inch deep.
A range of different kinds of components are on shortage for automotive vehicles. So automotive vehicles are now computers on wheels, right? And so there's a need for electronic components to manage sensors, to monitor, engine performance and all the subsystems. You have dedicated new infotainment and mobility and services that are emerging that are increasing the complexity and the density of any of these subsystems. And then you have some stuff that's like really basic engineering control units, ECUs, that really just are the brains of a car. Like, it's kind of getting much more pervasive. Everything's getting electrified. And so an automobile and the automobile industry has a high mix of components that they consume at relatively smaller volumes relative to, say, like a PlayStation or an Xbox that are also under constraints, that have a smaller dedicated bill of material, but use a lot of the same components like audio ICs and RF devices and transmission, et cetera. Like all of the communications components oftentimes are reused across many different applications. And so what we're seeing is this kind of shared set of common components got decommitted in automotive, consumed very quickly by these other industries. And because of that, the lead times have shifted from, say, 8 to 10 to 12 weeks out to 50 weeks plus. And so the recovery for automotive is really hard.
Another issue compounding the electronic sourcing dilemma in the automotive sector is the safety requirements that surround the automotive supply chain. Barnett pointed out that even if an alternative vendor did have available inventory, in many cases the auto manufacturer or tier 1 supplier would have to recertify their design based on the new part before it could go into production. And that is a process that can take years. Then throw a fire at Renesas's Naka automotive semiconductor manufacturing facility, and even the less publicized impact of the winter storms at Samsung and NXP factories in Texas. And all of a sudden, you're piling a lot of straws onto the camel's back.
In the automotive industry, and particularly in Japan, I mean, we've seen those stories even going back to sort of 3/11, the Fukushima plant meltdown, the impact on Sendai, all the automotive kind of cluster of suppliers there that were single source suppliers for a lot of automotive OEMs, shined a big spotlight on this problem and this challenge. But these issues are just normal. Overall, this just happens, right? That certain production lines will run down. We saw the winter storms in Texas, where I am, directly impact fab production at semiconductor suppliers Samsung and NXP. Also an unplanned event, weather-related, all adding additional shortage pressure and capacity pressures on the automotive industry. And so when you're in a constrained environment, all of a sudden, any external impact, even logistics and distribution impacts, all add up. And that's the challenge right now, is it's just a pressure cooker environment.
But what about stockpiles? Humans have been stockpiling goods since the dawn of civilization to protect themselves from the situations just like this. And in automotive, semiconductor inventory stockpiles are typically held at a key distributor or a tier 1 supplier to support just-in-time inventory at assembly plants. So, what's on hand?
You're typically seeing 4 to 8 weeks, 1 to 2 months worth of inventory on a normal level being managed upstream.
Barnett says,
in the case of Toyota, they have a trading company that's part of the Toyota group that specifically in Japan was maintaining up to 4 months worth of inventory as buffer inventory. But for other automotive OEMs in Germany, the US, you have less of that structured buffer management of key inventory upstream, and there's a greater reliance on tier one suppliers like a Continental or a Bosch or a Dentsu, or distributors, the normal mainline distributors that we work with, like Arrow and Avnet, to kind of buffer normally market inventory before you go back to the actual semiconductor suppliers themselves, which normally don't hold a lot of finished good inventory directly at their factories. So, there's on average, there's 4 to 8 weeks of buffer, but it only takes a relatively quick imbalance in the market for the average lead times to extend well beyond those buffer inventories.
What did we say earlier? That the lead times have shifted out to 50 plus weeks. 50 weeks minus 8 weeks. Carry the 2. Detroit, we have a problem.
From IHS, there was a general rough forecast that up to 670,000 vehicles may not be produced because of component shortages in 2021. Fitch and other rating agencies are looking at the potential forecast changes of OEMs in the automotive sector. That could actually increase to 1.5 million production vehicles. I think we still don't know what the total, actual shortfalls will be. But this is going to be one of the most significant electronic shortage related economic impacts of any industry we've ever seen.
There are ways that supply chains could have protected themselves from some of this risk. With insight into buying patterns via market intelligent platforms like Supply Frames designed to source intelligent software as a service offering, for example, OEMs and their suppliers could infer things about future market conditions by analyzing spot automotive electronics buys that started popping up in late Q3 and Q4 2020. By understanding that these actions meant a prolonged component shortage was likely on the horizon, automakers and their suppliers could have theoretically bet big on any available inventory. And, as Barnett notes, just having vehicles roll off the line could be a big factor in winning consumer confidence in the 2021, 22, and beyond. But realistically, many of the factors contributing to the shortage could not have been prevented, like a pandemic, a fire, and a snow and hail deep in the heart of Texas. So, that leaves us wondering, how long will this shortage last?
There's a process that will work itself out, over the next 9 months, 3 quarters to 4 quarters rolling into 2022, particularly for automotive. But I do think that we are seeing general fragility and capacity constraints in multiple areas of the electronics value chain, and just rising growth in consumption and electrification, if you will, of multiple downstream industries. So this kind of aggregate trend is continuing to increase, and I think there's an aggregate supply-demand imbalance that'll put pressure on different segments of the electronics value chain. We'll see move into different constraint-based situations potentially over the next couple of years and even into the future. I think what we saw happen with the pandemic is, in some ways, it exposed some of those overall constraints in the market, a lack of resiliency by many companies, particularly in automotive, but there's an aggregate level market challenge. And I think we'll see potential constraints in other segments that'll move like whack-a-mole. It'll move from microelectronics, microcontrollers and ICs into, say, different forms of passives, or indirect costs going up that may put pressure on both price and availability because of raw material input cost changes like resins impacting multiple segments within the electronics value chain. So I think we're entering a little bit of a new normal of a higher degree of volatility around lead time and price and cost for the foreseeable future.
Thanks for listening to this edition of Embedded Insiders. For daily industry news, videos, and podcasts, visit our website, embeddedcomputing.com.